then he returned to India, and today he's going to tell us about fluid gravity correspondence.
Do you know how I go up and down on this? Okay, thank you. Sorry for the technical incompetence. It's great to be here. It's great to be giving this talk. The talk is titled Fluid Gravity Correspondence, and I'll explain what that means. So we go on. The talk is these sections. I'm going to start with an introduction, then I'll give a lightning review of fluid dynamics, and even lightninger review of the ADS-CFT correspondence. Then talk about the fluid gravity correspondence. Talk about the uses that's been put to trying to develop fluid dynamics as an effective theory, and end with a teaser on new developments about the relationship between gravity and fluid dynamics on a sort of soap opera. Okay, so let's start. In this talk, I'm going to describe a precise duality between two of the best studied partial differential equations of physics. These two equations are on one end the Navier-Stokes equations, or more precisely relativistic generalizations and other generalizations of the Navier-Stokes equations. And on the other end are Einstein's equations of gravity. Okay? The study of this fluid gravity correspondence has had some applications. Surprising. It's led to the realization that the sort of quote-unquote standard equations of relativistic hydrodynamics, the equations you find in the textbooks of Landau and Lifshitz, are under certain circumstances incomplete, and has led to the completion of that framework, as I would like to describe. The so-called fluid gravity correspondence has also focused attention on an interesting problem, the problem of building an effective all-orders theory of hydrodynamics, and has helped make progress in that, as I will describe as we go. Okay, so let's start. To start this talk, let me start this talk with a very brief review of the formalism of hydrodynamics. Okay, let's take a simple situation where we're looking at the hydrodynamics of the effective hydrodynamics of a quantum field theory on some fixed background manifold. Let's take that to start with to be just flat space. Okay? The quantum field theory that we're looking at is very simple. It has a conserved stress tensor and eventually perhaps some conserved U1 charges. And in the thermal state, no like degrees of freedom other than those associated with conserved charges. I'll explain what that means as we go. Okay. So, in this simple context, the equations of hydrodynamics are so the hydrodynamics is an effective description of the dynamics of a nearly equilibrated quantum field theory. The variables of hydrodynamics are local versions of the parameters that parameterize equilibrium. So in the context that I talked about, these parameters are a temperature, a chemical potential, and a velocity. The temperature and chemical potential you're familiar with. The velocity field we don't normally talk about in thermodynamics, but because there it's a trivial degree of freedom. You can get it from no velocity to velocity by boosting. Okay? This velocity field is less trivial in dynamical situations because the boost here and the boost there may be different, and these relative velocities are physical. The equations of hydrodynamics are simply conservation equations. They're the equations that reflect the fact that the stress tensor of the theory is conserved in the absence of background fields, corrections to conservation equations in standard ways, or that the charge part of the theory is conserved, perhaps corrected by some sort of anomaly contribution. Okay. Now, I've told you what the variables of hydrodynamics are and the equations of hydrodynamics. However, the equations that I presented to you are given in terms of the stress tensor, not in terms of the variables of hydrodynamics that I listed, maybe the temperature, the chemical potential, and velocity. These two statements come together once you have constitutive relations that allow you to express the stress tensor and charge currents as local functionals of local values of chemical potential, local temperatures, and velocities. Okay? So if, please.
You assume that you are very close to thermodynamic equilibrium.
We're assuming we're very close to local thermodynamic equilibrium, and in fact, the structure of the equation of hydrodynamics is in a derivative expansion around that equilibrium.
So it's linear response to...
No, not, it's locally linear response, or whatever. But it can, over a long distance can be very far away. But locally linear. Yes. Okay. Okay. Now, this, you see, I'm addressing that question in this slide. As we've seen, the equations of hydrodynamics are simply conservation laws. And you might think that, conservation laws just follow from symmetry, so they seem a bit trivial. Something that I want to emphasize very much is that the content in hydrodynamics comes not so much from the conservation laws as from these constitutive relations that allow you to express the stress tensor and charge currents in terms of the variables of hydrodynamics, namely local tensor potentials, temperatures, and velocities. To emphasize how non-trivial this is, let's do some counting. Let's look at a stress tensor in a four-dimensional field. The stress tensor is a symmetric tensor, so it's 4 and 5 by 2, so 10 independent components. Conservation, on the other hand, is 4 equations. 4 equations don't determine the dynamics of 10 fields. So conservation is a constraint of field theory dynamics, but not an equation of motion for field theory dynamics. However, if for some reason these 10 different fields, the stress tensors, were all determined in terms of 4 functions, then the equations of conservation could become equations of dynamics. Now, so let's work with the situation where there's no charge. So we have only the stress tensor. The 4 fields in the problem will be the temperature, that's 1, and 3 velocities. Now, what is the physics that will allow you to determine these 10 different fields in terms of these 4 independent fields? And that's the physics of local equilibration. If you're in a situation where locally stuff is equilibrated, then the local properties of that stuff will be determined by local temperatures and velocities. The full 10 components of the stress tensor will be determined. Of course, the stuff is not completely locally equilibrated. Because complete equilibration assumes that everything's uniform. If stuff here and stuff here is different, it's not really. So the equations of hydrodynamics are equations that are written in an expansion around local equilibration, in an expansion in derivatives around local equilibration. Okay? So by its very nature, the equations of hydrodynamics are equations written in a derivative expansion. Yes, please. The chemical potential in the simple example I set it to 0. But if you had, let's say, one conserved charge, you'd have one extra variable, that's the chemical potential, and one extra equation of motion, namely charge conservation. So the counting is simple. Okay. So the key thing in hydrodynamics are these constitutive relations. These relations that, order by order in derivative expansion, allow you to compute what the stress tensor is in terms of the variables of local variables of thermodynamics. Now, in principle, you should be able to determine these constitutive relations by doing some calculation of the field theory. In strongly coupled systems, in practice, that's almost impossible. Even on the computer, it's very tough. Okay? And in practice, actually, the one exception to this is what I'm going to present. Using gravity, we can do this. But in practice, you often think of these constitutive relations as undetermined, fitting parameters that you try to constrain by consistency requirements. Okay? And these constitutive relations are really important because the equations of motion of our theory are specified only once we have them. Okay, so let's look at these constitutive relations in a little more detail. Let's first work at zeroth order derivative expansion. So we write down these constitutive relations, expressions for the stress tensor and the charge current without any derivatives. In that situation, if you work in zeroth order derivative expansion, you get the same answer as if you were in complete equilibrium. Because there are no derivatives, you can't tell the difference between things varying or not. Okay, so the constitutive relations are those of thermodynamics. The stress tensor is given in terms of pressure and energy density, and the charge current is given in terms of a charge current multiplied with velocity. It starts very simple. Already, this simple constitutive relation gives you interesting equations of motion once you plug it into conservation. These are the equations of perfect fluid dynamics. However, many important fluid phenomena in particular dissipation and production of entropy happen only at higher orders than the derivative expansion. So the stress tensor here is corrected at higher orders than the derivative expansion. There's the perfect fluid part plus some other stuff. Similarly with the charge part. It's the perfect fluid part plus some other stuff. And by its very nature, the theory of hydrodynamics is a theory of derivative expansion. So we should try to determine this other stuff order by order and derivatives. That's the aim. Okay. So let's first try to do some counting. Is this irritating? Sorry. Let's first try to do some counting. Okay. If you are an effective field theorist, the first thing that you might think of is, well, let me just write down all independent structures I could for pi mu nu, and all independent structures I could for j mu, things that just will match up indices with one derivative. And behind any of these structures, I can put an arbitrary function of temperature and chemical potentials. These are my free parameters. You might think that's the case, and if you did this counting at first order in the derivative expansion for charged fluids, you would find 5 parity even and 2 parity odd structures. If you think about it, first order derivative expansion is the famous order, the order where all transport coefficients occur. And if you think about it, you don't know 5 transport coefficients for charged fluids, certainly not 5 plus 2. And the reason for that is that this counting is an overcount in a way that we're going to get to in a bit. Okay, yes?
Just too many questions, I don't know where to start, but when one writes constitutive relations,
Yeah.
also constitutive constants.
Yes?
In the previous slide, which are the constitutive constants?
The constitutive constants, let's look first at these constants are functions of these constants are functions of temperature and chemical potential. Say your viscosity. The viscosity would be a term in pi mu nu proportional to sigma mu nu, where sigma is the shear. Now behind it, there would be what you might call a constant, but actually could be a function of temperature and chemical potential. So this constitutive function would be one of the things behind this structure.
So what are the fundamental fields and what are the constitutive relations?
The fundamental fields are simply velocities, so let's forget about charge flow.
Yes.
The fundamental fields are velocities and temperatures. These are the variables. Constitutive relations are the functional expressions that allow you to express the stress tensor order by order in a derivative expansion in terms of your fundamental fields.
So this I'm happy. And why isn't there a conservation law for the entropy, for example?
Because entropy is not always conserved, reduced.
No, so an equation of motion for entropy.
It's coming.
Oh,
Yes, but that would be not a fundamental thing, it would be an output of the game. Half output. You'll see. Okay. Anything else? Okay, right. Okay. So good. We've gone through our first part. That's on hydrodynamics. Now, thank you. Now a briefer review of the ADS. Okay. It has long been argued that UN theories, at least UN gauge theories, reduce to an effectively classical system in a particular large element, so a third large element. Okay. Now, this is supposed to be true for all reasonable UN gauge theories. There's a particularly interesting UN gauge theory, which happens to be very supersymmetric. It's called n equals 4 Yang-Mills theory. Okay, why these doesn't matter very much. It's a gauge theory based on the UN gauge. Okay, now n equals 4 Yang-Mills theories have many properties. In particular, they conformally invariant. There's a line of fixed points of theories labeled by constant coupling, constant blah. Now, in 1997, Maldacena identified the corresponding large N system, the classical system that generated the classical large N dynamics of this particular large N gauge theory. And the identification was a surprise. While the classical equations identified by Maldacena were unfamiliar and sort of complicated, and general values of the coupling constant of this line of fixed points, they became much simpler and larger. In the large lambda limit, these equations reduced to the equations of Einstein, more precisely, a supersymmetric generalization of Einstein's equations, equation for Einstein gravity and space-times that asymptote to AdS5 plus S5. Okay? So let me say it again. All large N systems have classical duals. This particular large N system has a classical dual. For most large N systems, we know that they have classical duals, but we don't know what they are. This particular system, we know what the classical dual is. Surprise, it's a theory of gravity. Okay? This is the famous AdS-CFT correspondence of Einstein. Okay, the gravitational description of field theory dynamics applies only at very strong field theory coupling. For this reason, this duality is hard to test. Because if you want to test it, you've got to know something independently on the field theory side at very strong coupling, which is sometimes possible, but often hard. Okay. However, there are some general expectations about field theory that are true even at very strong coupling. In fact, are true especially at very strong coupling. And one of these general expectations is that in appropriate circumstances, the theories equilibrate. And they equilibrate also locally. Okay, but let's start with just the fact that they equilibrate. So if Monsign's correspondence, the AdS-CFT correspondence is correct, which of course it is, you can ask the question, what is the gravitational description of the thermal state, the state of thermal equilibrium? This question was answered by Witten. And he explained that the gravitational dual to thermal equilibrium was a particular gravitational solution, not an ensemble of gravitational solutions. Okay? But a particular gravitational solution. It's called the black brane. It's a translationally invariant version of a black hole. Okay? Which does not exist stably in flat space, but exists beautifully and nicely and stably in AdS space. This answers the universality about it, but we forget. Okay, so just put a few equations to what I said. In appropriately chosen units, Einstein's equations for the negative cosmological constant in d+1 dimensions are these equations. If you just had Einstein's equations in flat space with no matter, you'd have this stuff equals 0, this stuff here is the cosmological constant. And this black brane solution that I was talking about is this solution. Okay? Suppose we're in 5 dimensions. Bulk dual to AdS to n equals 4 atmosphere is 5-dimensional gravitation. Okay? The 5 coordinates are a radial coordinate r, and then 4 field theory coordinates. The coordinates on which the field theory lives, and then an extra coordinate, which gravity has but field theory does not. Okay, this is this coordinate r. This function f of r here is this quantity here. Something you should note is that when r goes to infinity, f of r just goes to 1. If I just said f of r 1, this metric here is just a metric of AdS space. Okay? So we've got this, the solution here is what's called asymptotic AdS. In the sense that it differs from AdS, but reduces to AdS space at the boundary of space, namely, infinity. Okay. Now, near r equals infinity, this stuff is AdS space, but r away from infinity deviates significantly, and particularly significantly deviates at r is equal to pi t. D is just 4 here. D is the number of dimensions of the field theory. D is 4, so at r equals pi t, f of r goes to 0. And this metric looks like it's becoming singular. This is the kind of singularity we've seen before. It's the kind of singularity you have in the event horizon of short-shaped black hole. And this is just an indication that this metric here has an event horizon at this point. And this event horizon is translationally invariant. This is the black brane solution.
What is U in this equation?
What is U? Okay, excellent. U here, sorry, I should have written that. U here is any constant 4 vector.
Oh, thank you.
Okay? So, the simplest example would be U is equal to 1, 0, 0, 0. Okay? That would describe thermal equilibrium at rest. For setting U to be any constant 4 vector that's not 0 describes thermal equilibrium boosted at velocity. Thank you. Okay. So Einstein's equations allow us to study deviations from thermal equilibrium. The natural first question about if you study deviations away from thermal equilibrium would be what is the spectrum of fluctuations around thermal equilibrium? Small fluctuations. We know what equilibrium is. We've got dynamics around it. So let's compute the spectrum of small fluctuations. Imposing the appropriate boundary conditions, you can linearize Einstein's equations around the solution and find the spectrum of small fluctuations. And we get, at every spatial momentum k, we get, when you solve this problem, you get an infinite set of modes. sets of modes with omega, the frequency, as a function of which mode you're looking at k. Okay? Now, the general form of this omega as a function of k, by the way, omega is not necessarily real. In fact, it always has an imaginary part representing decay. Okay? The general form of this function is complicated. However, things simplify when the limit k goes to 0. In the limit k goes to 0, just from scale invariance, conformal invariance, scale invariance of the problem, all these omega n of k tend to some pure number which depends on n times the temperature. Okay? And there are 4 special modes here that are distinguished. For these 4 special modes, this pure number is 0. Okay? These are the lightest fluctuation modes in the problem. Okay? These are the modes that will cover long distance dynamics of the problem. Okay? I haven't written it here, but you can work harder and compute not just what happens at exactly 0k, but in an expansion 0k. Two of the modes are omega proportional to k. 2 of them are omega proportional to I times k squared by temperature. And okay, this is what you get from gravity. Now you can try to ask, what are our general expectations from field theory? Well, these fluctuations about equilibrium should be governed by the equations of hydrodynamics, the equations that we discussed in the first part of this talk. If you just plug those equations, look at the equations of hydrodynamics, linearize them, you find 2 modes that go like k, these are sound modes, 2 modes that get k squared by t, these are shear modes, and the structure completely matches provided you identify the viscosity of the field of the fluid by the entropy with the number 1 over 4 pi. If you work with a fluid which has viscosity by entropy ratio 1 over 4 pi, you will get exactly the constitutive relations you get out of gravity. This is the first indication that gravity is describing not just static properties around thermal equilibrium, but also dynamic. Okay, however, this indication is only linearized. Everything about my general philosophy is nonlinear. The equations of gravity are the nonlinear large-n description of the field theory. Hydrodynamics should describe long wavelength nonlinear dynamics of nearly thermalized stuff. Okay? So, if everything I said at the beginning is correct, and some indications are right,